Is our entire universe located in a black hole? And do we have to rewrite the theory about the origin of the cosmos and the history of the Big Bang? Precisely these are the questions that are currently being discussed fervently within cosmology and astrophysics, and the mathematical and physical calculations for it surprisingly look extremely good. Our Big Bang began with a singularity, an infinitely small, infinitely dense point in which matter is squeezed together. And in the center of black holes, we also suspect a singularity. But what if every black hole could be the entrance to its own universe? Was the Big Bang really not the beginning of space and time, but only the moment when the entrance to our multiverse was opened? I will address these questions in this video, distinguishing what facts we can separate from assumption, and everything about the Big Bang theory and black holes you will learn now. First, we need to understand exactly what black holes are and what they are not. Black holes are not vacuums that devour everything in their path. A black hole is, first of all, a celestial body in space with mass and volume, like any other body. For example, if our moon was replaced by a black hole of the same mass, almost nothing would change for us. The black hole would orbit the Earth, and there would still be tides, that is, ebb and flow, just as before. Only the moon would of course be missing at night, and also moon and solar eclipses would be passé. But just because one exists for our pet, it doesn't mean it destroys us. For that, it would have to have more mass than the moon. Then it could become dangerous for us. But what's special is that black holes have an extreme amount of mass in an extremely small space. A lot of mass, little volume. That means if you wanted to turn the Earth into a black hole, you would have to shrink it to about the size of a blueberry. A blueberry that weighs 6 trillion tons. And this is where it gets exciting. A very similar object that is relatively small develops special physical properties. The more mass a celestial body has, the stronger its gravitational force. That is, the gravitational force with which it pulls matter towards itself. And with that, the speed that one needs at least to escape from it also increases. The velocity with which one just manages to do this is called escape velocity. On Earth, for example, it's 11.2 kilometers per second. A spaceship must travel this fast to escape the gravitational pull of the Earth. A black hole can only laugh at that if it had a mouth. If you calculate the escape velocity from a black hole, you get values that are far above the speed of light, more than 300,000 kilometers per second. And since Einstein, at the latest, we know nothing can be faster than light. That means once you have crossed the so-called event horizon, the surface, or the boundary to the black hole, there is no turning back. That's why black holes are also black, because not even light can escape them. And inside a black hole, we probably expect a singularity, probably because we obviously have never been able to check. A singularity, as mentioned at the beginning, is an infinitely small point in which the entire mass of an object unites. That there are black holes, we have already proven. After all, we have even taken pictures of them. But what it looks like inside them, we do not know. Could it therefore be that a whole universe exists within the singularity? Let's take a closer look. The Big Bang theory, as we know it today, comes from the 1920s and comes from Belgian astronomer and priest Georges Lemaître. He assumed that our universe is not static, which was a widely held belief in the world of physics at the time, but that everything is moving away from each other. So, if you turn back the clock, everything must have been at one point at some time. Lemaître called this point the primeval atom. In 1927, he presented his calculations in Brussels. In the audience sat none other than Albert Einstein. He must have been quite nervous since his calculations were partly based on the formulas that Einstein himself had put into the world a few years earlier. But Einstein was initially not at all enthusiastic about the idea of the primeval atom and said to Lemaître, "Your calculations are mathematically correct, but your physics is abominable." At this point, it's important to talk about the term theory. We use the word in everyday life a bit differently than scientists do in their work. In science, an idea only becomes a theory when there is enough evidence for it. You can therefore make good predictions based on a theory that then also happen. An idea for which there is no or only insufficient evidence in the world of science is called a hypothesis. Lemaître's calculations were also first only a hypothesis. To turn them into a theory, they had to be tested and compared with the real world. Lemaître hoped for this by observing the night sky. His hope was fulfilled. In 1929, the American astronomer Edwin Hubble discovered that galaxies move away from us. The farther away they are, the faster they move away. Hubble concluded from this that the universe is expanding, and since galaxies are moving away from us, they must have been closer to us in the past. This observation fits perfectly with Lemaître's idea. In 1930, he also received support from the Soviet scientist Alexander Friedmann, who discovered the same thing independently of Lemaître. From then on, the model of the primeval atom was no longer just a hypothesis, but a theory, because it explained observations of the real world, and you could also make predictions with it, which then also occurred. And what predictions can you make with the Big Bang theory? For example, that the universe was extremely hot and dense at the beginning and has cooled down ever since. This is due to the expansion, because when something expands, it cools down. An example of this is a deodorant spray can. If you spray from it, the can becomes colder because the gas expands when it exits. The same principle applies to our universe. And indeed, in 1965, two American radio astronomers, Arno Penzias and Robert Wilson, accidentally discovered a residual heat from the Big Bang, a so-called cosmic background radiation. It's about 2.7 Kelvin cold, which is almost minus 270 degrees Celsius. In the following decades, other predictions of the Big Bang theory were also confirmed. The theory has so far withstood all tests, but it's not perfect. For example, it says nothing about what happened before the Big Bang. And here, black holes come into play. As already mentioned, we expect a singularity in their interior. But what does inside mean in this context? After all, a singularity is infinitely small. It doesn't really have an inside or outside. To explain this, we need to take a little excursion into general relativity, Einstein's theory of gravity. According to it, mass bends space and time. The more mass something has, the more it bends its surroundings. An often used analogy for this is a rubber sheet on which heavy balls lie. They push the sheet down and curve it. If you now roll a smaller ball past a larger one, it will not move in a straight line, but will follow the curvature. The same principle applies to our universe. Planets, stars, and also light move along these curves. If a lot of mass is now concentrated in a small space, as is the case with black holes, this curvature becomes extremely steep. So steep that beyond a certain point, not even light can escape it. This point is the event horizon. What happens inside it, we do not know exactly. But we have some models for it, and they say that behind the event horizon, the curvature becomes infinite. It forms a singularity. In it, all the mass of a black hole is united in an infinitely small point. That's at least the theory. Reality could be a bit more complicated. Perhaps singularities are not really infinitely small, but only very, very small. That would not change much in the practice, because they would still be so small that we could never observe them directly. But it would make the math a lot easier, because mathematicians do not like infinity. In any case, in a singularity, an incredible amount of mass is gathered in an incredibly small space. The laws of physics as we know them reach their limits here. And perhaps the singularity is not the end, but the beginning of something new. Maybe it's a doorway to another universe. This idea is not as abstruse as it might sound at first. There is a certain similarity between the Big Bang and black holes. In both cases, we are dealing with a singularity, and in both cases, we do not really know what that means. The English physicist Stephen Hawking has therefore suggested considering the Big Bang as the explosion of a supermassive black hole in a higher dimensional space. Our universe would then be a kind of bubble in this higher dimensional space. A similar model was developed by the American physicist Lee Smolin. He suggests that in every black hole, a new universe is created. These universes could have different physical laws. Some would collapse immediately, while others would expand indefinitely. Perhaps some of them would also produce life. This model even offers an explanation for why the physical constants in our universe are as they are. In universes with other constants, life might not be possible, so they could not ask why their universe is the way it is. We can do this, so we live in a universe that allows life. This is also known as the anthropic principle. This idea sounds very speculative, and it is, but it's not completely pulled out of thin air. There is some evidence for it. Black holes, for example, emit radiation. This was also discovered by Stephen Hawking, and it is therefore also called Hawking radiation. It arises from the so-called quantum fluctuations. According to quantum physics, particles and antiparticles are constantly being created and annihilated again in a vacuum. Normally, this happens so fast that we do not notice it. But if such a pair of particles is created near the event horizon of a black hole, it can happen that one of the particles falls into the black hole while the other escapes. The black hole then loses a tiny bit of mass, while a particle is created outside that we can observe as radiation. In this way, black holes slowly lose mass and finally evaporate completely. This process takes a very, very long time, especially for large black holes. Some physicists suggest that the escaping particles could create a new universe in a higher dimensional space. This universe would initially be very small and hot and would expand rapidly. Does that sound familiar? Exactly, just like the Big Bang. The universes that arise in this way could also contain black holes, which in turn spawn new universes. This would create a kind of multiverse, a collection of many universes with different physical laws. This model is still very speculative, and there is no direct evidence for it. But it is compatible with our current knowledge and cannot be ruled out. Whether it is true, we will probably find out in the next few decades. Until then, we will have to live with the fact that we do not know exactly where our universe comes from and whether it is the only one. But perhaps this ignorance is also a good thing. After all, it allows us to explore the cosmos and its secrets, and perhaps to find out more about our own origins.